All right. How's everybody doing today? Yeah, hanging in there? All right. Little chilly? Yeah. All right. So today we're going to start with a review of solar energy. So we'll talk about solar cells, solar panels, solar arrays, and then we're going to go on to our main topic for today, which is diodes and transformers. So diodes and transformers are two very different components, and so you might wonder why we're going to be looking at both of them on the same day. Well, it turns out that they're both very integral parts of power supplies, and we're going to be looking at power supplies in our next lecture. So today we're learning about diodes and transformers so that we know a little bit about these components so that we'll know how they work when we get to power supplies. So we'll first start with diodes. We'll talk about what they are, why they're important, and how we use them. And we'll do a couple of example circuits on the board to help us out. Then we'll go on to transformers. Again, talk about what they are, why they're important, and how we use them. And then we'll talk about a couple of specific concepts for transformers, including the turns ratio, step-up or step-down transformers, what a center tap is, and what it means to have an open winding. And finally, we will talk a little bit about voltage measurements. So these are just different ways that we can quantify voltages, okay? So we'll finish with that, and then we'll go on and do our lab preview for today. So are there any questions before we get started? Okay, cool. Then let's start with our review of solar energy. So we said that solar energy is energy that we get from the sun. And the basic component that we would have in a solar energy system is a solar cell. So the solar cell is made of two different types of silicon that are sandwiched together. This is the most common type of solar cell. One of those types of silicon has a chemical added to it that causes it to have extra electrons. The other side has a different chemical added that causes it to have holes or positive charges where electrons should be. So when you have a sun and the sunlight hits the negatively charged side of the silicon, that releases some of those extra electrons. And then if you take a wire and attach it from one side to the other, those electrons will flow through that wire in order to fill up some of those free spaces on the other side of your solar cell. And we said that this sandwich allows the electrons to flow from the positive side, from this side to the negative side. So when these electrons flow through this wire and they start to build up, they can actually migrate back to this side where they started off. So that's how the cycle continues. But this sandwich it only allows the electrons to flow in one direction. It actually blocks them. It prevents them from flowing the opposite direction. So that's why when you have extra electrons built up on this side, they can't just flow across the barrier to the other side. So
why do the negative charged electrons, why are they able to go across the middle that way? I know it's one way, but why can't the positive go the same way?
Right. So why don't the positive charges go?
Yeah.
Yeah, I see what you're saying. So the positive charges are essentially holes that are left behind when the electrons go away. So yeah, so that's what happens. So the electrons can flow across, and then when they go across, they leave these holes behind. But the electrons cannot go back the opposite way. And incidentally, this is actually the same type of sandwich, the same structure that is used to make diodes that we're going to be talking about today. So diodes are, the main purpose of a diode is a one-way valve for electricity. It allows electricity to flow through in one direction, but it blocks it from flowing the opposite way. So diodes are made in exactly the same way. They're made of a sandwich of two types of silicon, just like this. Okay? So that's what a solar cell is. And if you want to do something useful with the solar cell, then you put your load in the middle of this wire so that the electricity has to flow through your load in order to get back to the opposite side of the cell. And then it will power whatever you want it to power. So the load could be a battery that you want to charge, or a motor that you want to turn, or a little LED that, flashlight that you want to turn on. Whatever it is, you can make the electricity flow through it. So that's what a solar cell is. So any questions about that? Okay, so a solar cell by itself creates this energy, but it doesn't create very much. It has maybe about half a volt and maybe 10 to 100 milliamps of current, depending on the size of the cell. So it creates energy, but a very small amount. So if you want to do anything useful, you have to put these cells together. You have to combine several of them in order to increase the voltage and the current. So we said that there were several different ways to combine the cells. So how could you put cells together if you wanted to increase the voltage?
Series?
That's right, in series. So imagine you have one cell here that is producing 0.5 volts and 10 milliamps, and this cell has a positive side and a negative side. If you put two of them together in series, then you have increased the voltage to 1 volt total, because you've got half a volt there and then half a volt there. And so together you end up with 1 volt. And you can do that as many times as you want to bump the voltage up as high as you want. So in series, the voltage increases. But let's look at the current. Each one of these cells produces 10 milliamps. So that means that it needs to have 10 milliamps flowing out and 10 milliamps flowing back in. So this first one would have 10 milliamps flowing out, and then that same 10 milliamps would flow into the second one. And then the second one would have 10 milliamps flowing out. So altogether, you'd have 10 milliamps flowing out of your circuit, and then you'd have that it would go through the load and then come back, so you'd end up with 10 milliamps flowing back into your circuit as well. So each cell produces 10 milliamps, and the total circuit produces 10 milliamps as well. So are you increasing the current by putting cells in series? No, it stays the same. So in series, the voltage increases, but the current stays the same. Now, what could we do if we wanted to increase the current?
Parallel.
Yeah, we put them in parallel, exactly. So in parallel, you could have the same cells, 0.5 volts and 10 milliamps. And then we could have our load over here. Now, we could call this point ground, and we know that there's 0.5 volts across each one of these cells. So we got 0 volts there, and we go up by 0.5 volts, so we have 0.5 volts there. Now, we know that along a wire, the voltage is constant. So if we have 0 volts at that point, what voltage do we have at that point over there? 0 volts, exactly. It's connected by this wire to 0 volts over there, so we have 0 volts over there. And up here, we have 0.5 volts, and that's connected by a long wire over here. So what's the voltage at that point there? 0.5 volts, exactly. So across our load, we have 0.5 volts, just like each cell is producing 0.5 volts. So in parallel, the voltage, does it increase? No. The voltage stays the same. But now look at the current here. So each one of these cells produces 10 milliamps. So we get 10 milliamps flowing there, and that comes along to that point there. And then we get another 10 milliamps flowing out of that cell. So these two currents combine. So how much current do we have flowing down that wire there? 20 milliamps, exactly. And that flows out and flows through our load. And then it flows back along the bottom here. And then how much current is going to flow back into this cell?
10 milliamps.
10 milliamps, exactly. Whenever you have a current source, the amount of current going back in has to be the same as the amount of current coming out. So we've got 10 milliamps coming out. We better have 10 milliamps going back in. So we had 20 milliamps flowing along this wire. 10 of it goes up into this cell. So how much is left going this way? 10, exactly. So we get 10 milliamps there, and that flows back around and comes back into this cell over here. So in parallel, the voltage stays the same, but the current increases. The current through the load increases. So that's how we can put cells together to increase our current. Now, what if we wanted to increase our voltage and our current? What could we do then? Yeah, series parallel, exactly. So we could put cells together in series to increase the voltage, and then combine them in parallel to increase the current as well. So let's say we wanted 1 volt and 30 milliamps. Well, what could we do? We could have, in order to get 1 volt, we could have 2 cells in series. And when we put those together, we end up with 1 volt and how much current? 10 milliamps, exactly. So you could think of this column almost as a little pseudo cell that produces 1 volt and 10 milliamps. And so if you wanted to increase the current, you could just put 3 of these little pseudo cells together in order to end up with 30 milliamps. So you would get 10 milliamps from this one, and then you could do the same thing over here. And then one more time. And then that would give you 1 volt and 30 milliamps that could flow through your load over here. So any questions about that? Okay, cool. So this is how you can put cells together in order to create panels. But you can use exactly the same logic to put panels together in order to create larger arrays. So you use exactly the same procedure. You would just, the voltages and the currents that come out of panels would just be larger than those that come out of cells. And you can use exactly the same logic to put batteries together in order to create larger arrays of batteries to increase the amount of voltage and current that you get from those batteries. So, for instance, one AA battery has about 1.5 volts and maybe 100 milliamps that it can provide. So if your toy needs, your little remote control car needs, 6 volts, then you could put 4 of these batteries together in series. And this is almost always what happens inside of little battery packs. So you've probably seen little battery packs inside of various electronic equipment, and the batteries are all packed in there, like this. Well, what's really going on is that those batteries are being put together in series. So if you look closely, normally what you'll see is there'll be one wire coming out here, and then there will be a little metal connector between those 2 terminals, and a little metal connector between those 2 terminals, and then the other wire will come out over there. So what you've really done is you put these batteries together in series. You've connected the negative end of one battery to the positive end of the next, and so on. There'd probably be one more connector there, and then the other wire would come out there. So yeah, you've connected the positive end of one battery to the negative end of the next, and you've done that for all 4 batteries, so that increases the voltage of your circuit there. Okay? So the same logic applies for cells, for panels, and for batteries. So any questions about that? Okay. All right. So that was our review of solar energy. That's what I wanted to say about solar energy. So then let's go on to our main topic for today, which is diodes and transformers. So again, these are 2 very different components, and the reason that we look at them both in the same day is because they both are integral parts of DC power supplies. We'll be looking at DC power supplies in our next class, so this is kind of an introduction so that we learn about these components so that we can understand them, and then next time we'll see how we can put them together to make DC power supplies. So let's start with diodes, what they are, why they're important, and how they work. So a diode what is it? Well, the main function of a diode is that it's a one-way valve for electricity. It allows electricity to flow through in one direction, but it blocks it from flowing in the opposite direction. If we were to actually look at a diode, it's usually a little cylinder and it has typically a stripe on one end. So usually most of the body is colored in black, and then there's a little stripe that is white, that's or silver on the most common type of diodes. And these diodes can be very small if they're going to fit inside of a little phone or a little piece of electronic equipment, but they can also be quite large if they're going to be used in industrial machinery. So I'll pass around a couple of these diodes. You can take a look at them. Some of them have bodies that are made of silicon. One of them that's going around actually has a body that's made out of clear glass, so you can see through it a little bit. If you look at a symbol for a diode, it looks like this. You'll notice that the stripe on the symbol is on the same side as the stripe on the package. So if you're looking at a circuit diagram and you want to build that circuit with a real component, you figure out which direction the stripe is pointing in the schematic, and then you make sure that the stripe on your diode is facing in the same direction. So the two ends of the diode actually have their own names. So this end is called the anode, and that's abbreviated with an A. And the other side is called a cathode. And this was examined by engineers who promptly abbreviated that with a K because engineers can't spell. So we got the anode and the cathode. And if you want electricity to flow, then you put a positive charge on the anode and a negative charge on the cathode. And when you do that, we say that this diode is forward biased. And when it's forward biased, the electricity flows. And the voltage across the diode is approximately 0.6 volts or 0.7 volts, somewhere in that range. Now this is different than resistors and other types of components that we've seen. Remember, with resistors, the more current is flowing through a resistor, the higher the voltage is. That's what Ohm's law says. Voltage is current times resistance. So as your current increases through a resistor, your voltage increases. But that's different here. Here, we're saying that when the electricity is flowing, the voltage is pretty constant. It's always about 0.6 or 0.7 volts. So you could have a little current flowing through there, it'd be about 0.6 volts. You could have a lot of current flowing through there. It could still be about 0.6 volts. So this voltage is relatively constant, independent of the current. Okay? Now, if you have the opposite voltage on a diode, so you've got a negative voltage on the anode and a positive voltage on the cathode, then we say that the diode is reverse biased. And no electricity flows, so there's no current through the diode. And the voltage across the diode is equal to the applied voltage. So that means that if you had a circuit and your power supply, it had a diode that was reverse biased and your power supply was giving you 5 volts, then you'd have 5 volts across that diode. If your power supply was giving you 10 volts, you'd have 10 volts across the diode. The power supply is your applied voltage. So whatever voltage you apply to when you have a circuit with a reverse bias diode, that voltage goes across that diode. Okay? So that's what diodes are. We never really talked about why they're important. Basically, the reason that they are important is because this property can be very useful for a number of things. So in our next lecture, we'll see how we can use this property to rectify alternating current. That means turn alternating current that goes positive and negative into a constant voltage or a constant current that is just positive. So that's one example of how these can be useful. Another example of how diodes can be useful is that they can be used in a protection circuit. So, for instance, if you have a little chip that's very sensitive and it can withstand voltage that's applied in the correct direction, but maybe that chip would blow up or get damaged if the voltage was plugged in backwards by accident, you can use a diode to protect that chip. So you can put a diode in there that allows the electricity to flow through when it's plugged in the correct direction, but blocks that electricity if it got plugged in backwards accidentally. So diodes can be very useful that way as well. So those are a couple of uses for diodes, and those are a couple of reasons why they're important. Another important use for diodes is LEDs. So an LED is a light-emitting diode. And the symbol for an LED looks just like a regular diode symbol, but it has a little arrow coming out to symbolize light. LEDs are one-way valves for electricity, just like every other diode. The difference here is that when electricity flows through an LED, that LED creates light. Okay? Also, the chemistry inside of LEDs is a little bit different than the chemistry and materials that are used inside of other types of diodes. So that means that the forward bias voltage for LEDs is different. So on red LEDs, the forward bias is somewhere around 1.8 volts, something like that. Turns out that the different colors from other LEDs are created because they have different materials inside them. And so those different materials actually create different voltages. So a red LED might have about 1.8 volts. You know, a blue LED might have closer to 2 or 3 volts. And then some of the purple ones might get up into 4 volts or even higher. So, so that forward bias might be different depending on what color of LED you have. But really, an LED is still a diode, and so if we learn about diodes, we can learn about how to work with LEDs as well. So, so that's why LEDs are important. Thank you. So in terms of how they work, I want to show you a couple of example circuits, and we can figure out how to analyze those circuits. So let's say that we had a power supply here, and say this was a 5-volt power supply, and we've got a diode here and a resistor. And we want to know how much voltage we have across our resistor. So let's see if we can figure out what this voltage would be. So first of all, let's look at our diode here. So is this diode, we've got a positive voltage on the anode and a negative voltage on the cathode here. Is this diode forward biased or reverse biased? Forward biased, exactly. So how much voltage is going to be across this diode?
5 volts. Or is it 0.6 or 0.7 volts of the applied voltage?
Yeah. So right. So it's about, we'll call it 0.6 volts. Okay. Since it's forward biased, we have about 0.6 volts. So we know we have 5 volts total. 0.6 of that is across this diode. So then how much of that would be left across this resistor down here? Yeah, 4.4 volts, exactly. So there we go. So then could we figure out the current through this whole circuit? Yeah, because now we know the voltage and we have a resistor, so we can just use Ohm's law, right? We would say I equals V over R. So that's 4.4 volts over 1,000 ohms. So that comes out to be 4.4 milliamps. Okay? So we'd have 4.4 milliamps flowing through there. And since this is a series circuit, we'd have the same current flowing through there. And yeah, the whole way around. Okay? So any questions about that? All right, cool. So that's how we can figure that out. Now let's look at a similar circuit. So we've still got a 5-volt power supply. We've still got our resistor here. we've still got a diode, but now the diode is facing the opposite direction. So now we have a positive voltage on the cathode, a negative voltage on the anode. So is this diode forward biased or reverse biased?
Reverse.
Reverse biased, exactly. So is the electricity going to flow through that diode? No, exactly. Exactly. So, so there's no electricity flowing through that diode. So in other words, there's no current. So we could say that the current flowing through this resistor is 0 milliamps. So if we have 0 milliamps flowing through that resistor, how much voltage are we going to have across that resistor there? 0 volts, exactly. So we've got 0 volts there. We know that we have 5 volts total. 0 of it is across the resistor, so how much of it is across the diode? 5 volts, exactly. So that's why you get all of the applied voltage across the diode when the diode is reverse biased.
What would be the purpose of doing something like that?
Well, so again, this could be like in a protection circuit. So when the voltage is plugged in the correct direction, the diode is reverse biased, and none of the current flows through there, and maybe your load is over here. So none of the current flows through the diode, and all of it goes through the thing that you're trying to power over here. If somebody were to accidentally plug in the power backwards, then this diode would become forward biased, and the electricity would flow through that diode and not damage the rest of your circuit. You only get about 0.7 volts, 0.6 volts across there, and hopefully that would be small enough not to damage the rest of your circuit.
Is there any way to have a diode that you can, like, switch?
No, not really.
And why do you get the diode facing backwards, but on there the reverse one doesn't face backwards?
Well,
It doesn't matter or no?
well, over here, what I showed is that the voltage is been reversed on this diode. So over here, yeah, the negative voltage is on the anode, and the positive is on the cathode. Yeah, yeah. The other reason you might have a diode that's reverse biased, at least part of the time, is in a power supply circuit, like we're going to talk about next time. So with power supply circuits, the incoming electricity is positive for part of the time and then negative for part of the time. And so you can have a diode, some diodes that allow electricity to flow through when the incoming voltage is positive, and then other diodes that allow electricity to flow through when the incoming electricity is negative. So we'll talk about that more next time. Yeah. So let's do one more example circuit. And this one will do an LED. So this is a common thing that you might want to deal with. So you might have a 5-volt power supply here, and then over here you could have an LED. So it's a diode that emits light, and then you could have a resistor. And let's say that you read the specification sheet for this diode, and it says that the diode can handle a maximum of 20 milliamps. And also, the spec sheet says that the forward bias for that diode is 1.5 volts. So then your job is to pick the resistor value that will give you 20 milliamps and 1.5 volts, or 20 milliamps maximum through that diode. Okay? So let's try and find that resistor. This is a common thing that that you might have to do if you're trying to build your own circuit with an LED. The spec sheet will tell you what maximum current is, and usually what the voltage is. So, yeah, this is something you might actually want to figure out. So, so what would be the first thing that we could do if we were trying to figure this out?
Just find the total resistance that we're looking for by using Ohm's law, right?
Sure. So, yeah, so for Ohm's law, you need, if you're trying to figure out the resistance, you would say R equals V over I. So you would need the voltage and the current. So how could we figure out one of those here for that resistor? Yeah.
You subtract 1.5 volts from 5 volts.
Yeah, exactly. So we know we have 5 volts total. 1.5 of that is up here. So the rest is going to be down there. So 5 minus 1.5 gives us 3.5 volts. Okay, perfect. And then how could we figure out, so we know the voltage now, so what is remaining is the current. How could we figure out the current for that resistor?
We use the 20 milliamps.
Exactly. We know that 20 milliamps is going to be flowing through this LED, and that current only has one place to go. It all has to go through this resistor. So then all of that current must be going there. So then the current there would be 20 milliamps. Perfect. So now we know the voltage and the current, so we can figure out the resistance. So that would be, the voltage would be 3.5 volts, and the current would be 20 milliamps, or 0.02 amps. So what's 3.5 over 0.02? What's that?
175.
Okay, so 175 ohms. So that would be the resistor that you would use if you wanted to have 20 milliamps flowing through this LED. So that's how you could figure that out. So any questions about that? Cool. Okay, so that's what I wanted to say about diodes. We said that they're one-way valves for electricity, and they have this forward biased voltage that doesn't change very much regardless of the current that's flowing through them. And we did a couple of example circuits there. So then let's go on and talk a little bit about transformers. So transformers a transformer is a device that changes the voltage and current of an AC signal. These only work on AC signals. They don't work on DC. Okay, so AC is a signal that is changing. It's going positive and negative. So transformers only work with AC signals. So that's what they do. What they really are is very simple. They're just two coils of wire that are close to each other. That's all it is. This first coil is called the primary coil, or just primary for short. And the other coil is called the secondary. And what happens is that when you put electricity through a wire, what is that, through a coil of wire, what does that coil of wire become? Yeah, an electromagnet. So electricity creates a magnetic field, and it turns out that a changing magnetic field also creates electricity in a coil. So you put electricity through this first coil, it creates this magnetic field, and then that magnetic field creates electricity in the second coil. So that's what transformers are. It turns out that a metal rod will help to direct that magnetic field. So oftentimes transformers are wrapped around or through a metal form to help direct that magnetic field from one to the other. And if that's the case, we call that an iron core transformer. And the symbol for an iron core transformer looks like this, same as normal, but it's got two lines in the middle to represent that iron core. If there are no lines in the middle, we call that an air core transformer. It's just wrapped around air. Okay.
Why is those the only option? Why don't they try to, like, what does the iron do itself?
So you remember when we created an electromagnet, I made the electromagnet by wrapping the wire around a big iron nail.
Yeah.
So what happens is that big piece of iron kind of directs that magnetic field in one direction. If that iron is not there, the field kind of spreads out and is less concentrated. That piece of metal acts to concentrate that magnetic field in one place or one direction.
Can you use another type of material?
I suppose it could be another type of magnetic material, but typically it's iron, just because it's common and it's relatively inexpensive. Yeah, and I don't think that other metals that are non-magnetic would work. Yeah. There are sometimes people want to make the core into like a donut. This is actually a fairly common thing. It's a donut shape. It's called a toroid. And those can be made out of like a ceramic that has iron embedded into it. So you'll have like a donut here. It's made out of this ceramic and iron material, and then the wire will be wrapped around it, something like this. You might have one wire on one side and then another wire on the other side. Something like that. So that's a fairly common configuration, but again, it's the iron in the donut, in the toroid, that is doing the work there. Yeah.
So then it's ceramic with an iron core.
Well, it's ceramic with iron mixed into the material. Yeah. Yeah. Yep. So
Is there a benefit to that that method? Is it like
the toroid rather than the I'm not sure exactly. I think that there must be, different trade-offs for different geometries, but I don't know exactly what they are.
How do you spell toroid?
I think it's Toroid. There could be a double R. I'm terrible with spelling, so it's something like that. Yeah. Yeah, other questions? Okay. So, all right. So that's what transformers are. Let's talk about why they're important. These can be useful for a variety of things. So oftentimes you want to change the voltage of a signal that you have, or an electrical source. So for instance, when we were at the powerhouse, the Folsom Powerhouse field trip, we saw that they had big transformers outside of their power generating facility. And the reason is that they wanted to take the electricity that was coming out of their powerhouse and increase that voltage to send it down the power lines, because power transmission is more efficient at high voltages. So they wanted to take that electricity that was coming out of their powerhouse and increase the voltage in order to transmit it more efficiently. Also, you might want to do the opposite when the electricity gets to your house. So if you've ever looked up at a power line, and you might see some wires running down it, and then on the power pole itself, next to or near to a house, there are often these big metal cans. And the metal cans have wires coming in from the power lines, and then they have other wires that go out to the house. Well, these metal cans are transformers, and what they do is they take the high voltage that's running on the wires, that's maybe 10,000 volts, and they step it down, they decrease it to the voltage that will go to your house, which is about 120 volts AC. So they go from thousands of volts down to hundreds of volts to make it more safe. So so that's one example. And then another example is when you have the 120 volts coming out of your wall, and you want to step it down to maybe 5 volts that you would use to charge your phone. Like when you have a USB charger, the electricity coming out of that is 5 volts. So you need another transformer inside of your power supply that takes that high voltage from the wall and steps it down to a lower voltage that you can use to transform or to power your electronic devices. So those are a couple of examples where transformers can be useful. That's why we care about these.
So is a power brick just a transformer that you plug into a wall to charge your phone?
So that's half of it, and then the other half is the rectifier that takes the lower. So the transformer takes the high voltage AC and turns it into a lower voltage AC, and then our electronic devices typically run on DC power. So you need to take that lower voltage AC and then change it to a DC signal in order to power the device. So the rectifier is what does that changing. And yeah, we'll talk about those more in the next class. But yeah, that's what goes on. That's what's inside of those power bricks. Yep. All right. So those are a couple of examples of where transformers are useful. So let's talk about the turns ratio. So the turns ratio is the number of turns on the secondary coil divided by the number of turns on the primary coil. So, so why is this important? The turns ratio actually determines how much the voltage changes. So if you have say you have a 2-to-1 turns ratio, that means you have twice as many turns on the secondary as on the primary. The voltage out is twice as big as the voltage in. So this turns ratio determines how much your voltage changes. So a 2-to-1 ratio multiplies the voltage out by 2. A 4-to-1 would increase the voltage by a factor of 4. 10-to-1 increases it by a factor of 10. So the turns ratio is what determines this. So you might be thinking, hey, I don't have to go to school anymore. I'll just put a couple of these transformers together. I'll take the 120 volts that's coming in. I'll make 1,000 volts. I'll sell it for 10 times as much, and I'll get rich, right? Sounds pretty good. Right. Unfortunately, well, yeah, no, unfortunately, there's no free lunch, okay? So the thing is that the power out of a transformer equals the power in, okay? So you can't make more power coming out than you have coming in. And remember, power is voltage times current. So what that means is that if you boost the voltage by a factor of 2, that means that the current gets cut down by a factor of 2. Yeah. So if you have a 2-to-1 voltage or turns ratio, the voltage out is twice the voltage in, but the current out equals half the current in. Okay? So as the voltage goes up, the current goes down, and vice versa. If you have a transformer that creates less voltage coming out, it actually creates more current than you would get into that transformer. So it's a trade-off, okay? You're trading voltage for current. That's what the transformer does.
So current and voltage. Voltage is what are this is kind of a bad question. I'm just confused on it. What is the use case of current? Like voltage is the power that goes into your phone. What is current used for?
So current is the amount of electricity that is actually flowing. So
Is it the speed?
I mean, it's the number of electrons that move past a certain point.
Okay. But
So-
what would the difference between someone getting 0.5 volts with 10 milliamps and 0.5 volts with 100 milliamps? Like what would the noticeable difference be?
Well, one thing is safety. So higher voltages can be dangerous for people. So if I have a power source that's providing 10 volts, I can grab onto the two leads and nothing's going to happen to me. If I have a power source that's providing 100 volts and I touch the two leads, I'm going to get a shock, and that's going to hurt. So in terms of safety, you want to have lower voltages. but again, in terms of efficiency, you want to have higher voltages. So that's actually where that, a long time ago when electricity was first being mass produced, there was this big war between Thomas Edison and Nikola Tesla. And Edison was pushing for DC electricity to be used all over the country, and Tesla was pushing for AC electricity to be used. Edison was saying, no, we should use DC because that's what most electronics run off of, and it's safer. We can use these low voltages with the DC, and it's great. Problem with that was that the electricity was there was very low efficiency. So when you would transmit that electricity maybe a mile, you'd lose like half of the power that you put in. So you were getting 50% losses over just a couple miles maybe. And so it just wasn't economically feasible. And the reason that they couldn't increase the voltage very well is because transformers only work on AC signals. They don't work on DC. So Tesla said, no, we'll use AC, and then we can use these transformers, and then we can take that AC signal and bump it up. We can easily change the voltage when we transmit it, and then easily change it when we get to the house and lower that voltage over there.
So current affects efficiency?
So yeah, essentially if you have, the more current you're trying to transmit, the less efficient your system is going to be. So instead of transmitting lots of current, the AC signal, you can increase the voltage on an AC signal, decrease the current, and then be more efficient. Yeah. So that's what's going on there. So yeah, you're trading off voltage and current. So step up and step down. A step up transformer is a transformer that has more voltage out than voltage in. So step up transformer increases voltage and therefore would decrease the current, whereas a step down transformer it decreases the voltage, but would therefore increase the current. Now there's a special type of transformer called a center tap transformer. So a center tap transformer the primary coil of a center tap transformer is just like on a normal transformer. So a primary is just a big coil of wire. Secondary is also a big coil of wire, but it's got one addition. It's got an extra wire attached in the middle of the secondary. So this is called a center tap transformer. Because it's got this center wire attached to the secondary coil. And what this does is that it gives you an extra voltage there. So say you were going to get 10 volts out of this entire secondary coil. What happens is that you end up with 5 volts between the bottom and the center tap, and then another 5 volts between the center tap and the top. So it kind of splits the voltage and gives you access to the voltage right in the middle there.
Does that offer like more control?
Well, so it can have a couple of different uses. So we'll see how this can be used in one of the power supplies that we'll talk about next time. Also, say you have a computer that needs different voltages for different things. Maybe it needs 3.3 volts for the processor, and it needs 5 volts for some of the LEDs, and maybe 12 volts for the fan. What you can do is you can have a secondary coil that has several taps on it. So let's say the maximum voltage that you need was 12 volts. So you would arrange it so that you got 12 volts out of the whole coil there. But then you wanted to have 5 volts for one of the other components. So you could put a tap in there that gave you close to 5 volts, and then another one a little bit lower that was 3.3 volts. So you can put these different taps in there to give you the voltages that you need.
How do they have a decreased amount of voltage? Is there like resistor?
No. So yeah, essentially. Yeah. So say it's like a turns. It is the turns ratio. So say you had a primary coil here, and the secondary coil. If you look at the full secondary, it might have 120 turns on it, and that would give you 12 volts. This part between there and there would only have 50 turns, so that would give you 5 volts. Yeah. Yeah.
Does the turn ratio work the same for step-down transformers as for step-up transformers?
Yes.
So would a ratio of 1 to 2 have voltage?
Yes. Yeah, that's exactly right.
Thank you.
Mm-hmm. Yep. Yep. So that's what a center tap is. So questions about that? All right. And then the other term I wanted to mention was an open winding. So if so an open circuit is just a circuit with a break in it. An open winding is the same thing. It's a winding that has a break in it. So if we say that there's an open winding, it just means that there's a break in one of the windings. Okay? So questions about that? All right.
Is the center taps, is it always the secondary that's tapped like that?
Yes.
Okay.
Yeah. All right. So then finally, the last thing I wanted to talk about before our lab preview is just some different ways of quantifying AC voltages. So when you're measuring a DC voltage, it's pretty straightforward. So a DC voltage is a voltage that doesn't change over time. So it's just a constant voltage. So if this is 5 volts, then it's 5 volts now, it's 5 volts in a minute from now, it's 5 volts tomorrow. It's just constant. So there's only one way of really measuring it. AC voltages are a little bit different. An AC voltage is a voltage that changes over time. So an AC voltage goes up and is positive for part of the time and then goes negative, positive and negative, and so on. And it turns out there's actually several different ways of of quantifying an AC voltage. So one common way of looking at it is called peak to peak. So that's the voltage between the highest peak and the lowest peak. So that's sometimes abbreviated VP-P. So maybe this is, so say this highest voltage there is 10 volts, and the lowest voltage here is minus 10 volts. So then what would the peak-to-peak voltage be in this case?
10 to negative 0.
So yeah, it's the voltage difference between 10 and minus 10. So that distance from 10 to minus 10, yeah, 20 volts. So we would say that this, you could call this signal 20 volts peak to peak. Another way of quantifying this is just looking at the highest point on that signal. So from the middle to the highest point, we would call that peak voltage. So what would the peak voltage be in this case?
10 volts.
10 volts, exactly. So that's another way of saying this. So if you said the voltage is 10 volts peak, that's equivalent to saying it's 20 volts peak to peak. Okay? But there's yet a third way of quantifying this voltage. And this third way came about because people wanted to have some sort of comparison between DC voltage and AC voltage. They said, okay, we're familiar with DC voltage. Let's say we put 10 volts DC into a heater. We want to kind of figure out, we can measure how much heat comes out of there. Now we want to kind of figure out what would the equivalent AC voltage be that would give me the same amount of heat. Okay? They wanted to kind of find this equivalent between these two different kinds of voltages. So what they did is they came up with this other measurement, which is VRMS. It stands for root mean square. So for an AC signal, VRMS equals 0.707 times V peak. So for this signal, that would be 0.707 times 10 volts. So that would be about 7.07 volts. So this signal would be 0.707 or 7.07 volts RMS. So what that's saying is that if you put this signal into a heater, you would need about 7.07 volts DC to give you the same amount of heat as this AC signal, which is 7.07 volts RMS, or 10 volts peak, or 20 volts peak to peak. These are all equivalent ways of saying what this voltage is. Different ways of describing the same signal here. Okay? Yeah?
Where'd that number come from? 0.707.
So it turns out it's 1 over the square root of 2.
Oh.
Yeah. So yeah, it's approximately 0.707. So that's, you just use this conversion factor if you want to get, if you want to figure out what that voltage is. So if you're looking at a meter and you're reading AC voltage off of that DMM, and it tells you, AC voltage, which one of these standards do you think they use? You think they use the easy one because it's super easy to understand? I wish it were the case, right? No, turns out that most meters use RMS. So when you hear that the electricity coming out of the wall is 120 volts, that doesn't mean that it's 120 volts peak to peak or even 120 volts peak. It's 120 volts RMS, okay? So, so what that means is that right there on the signal is about 120 volts. So the peak voltage would be V peak is 120 volts divided by 0.707. So it's something like 185 volts peak. So if you were to measure the highest voltage here, it'd be something like 185 volts. And if you were to measure the peak-to-peak voltage, that would be twice of that. So that's what? 85 times 2 is 170. So 370 volts peak. Okay? So 370 volts from the top of the voltage to the bottom. So the voltage coming out of the wall is actually 370 volts from the highest point on the signal to the bottom. So it's actually pretty large. But we think of it as 120 volts because that's what it is, RMS. Okay? So it's just a weird standard, but that's what's used most commonly. Yeah?
You said this is when talking about like voltage coming out of the wall and everything.
Yeah. So when we talk about the voltage, common power that we have in our walls, we say it's 120 volts. But that's 120 volts RMS, which means 185 volts or so peak, which is the same as saying about 370 volts peak to peak. Okay? So that's what's going on there. So questions about that? Yeah.
The 0.707 is just the relative amount of power that you need in DC compared to AC?
So yeah, what it means is if you put a signal that's an AC signal into a heater that's 10 volts peak, you would need about a 7.07 volt DC signal to match the heat that's coming out of that heater. Okay. So yeah, it's kind of a way of comparing apples and oranges that does, makes them somewhat similar. Yeah?
So does that mean it's become a weird unit like horsepower that doesn't actually reflect what it was supposed to begin with?
I mean, it does. It is a weird unit, but it does provide this sort of way of comparing AC and DC power. So if you put 7.07 volts of DC into a heater, you will get out the same amount of heat as if you put in 10 volts peak AC. In fact, if you look at fancy DMMs, they will say that they have a true heat RMS true heat RMS measurement or something, which means they actually have a little heater inside there. They're actually using that to calculate the RMS voltage from a signal. So yeah. So it's still done. That is the comparison there. Yeah. And this conversion is true for sine waves. If it were a different type of wave, like a triangle wave or a square wave, you would have to use a different conversion factor here. But this is for sine waves. All right. So So that's what I wanted to say about voltage measurements. So then let's go on and do a preview of today's lab. Okay, so the first part of the lab says that you're supposed to open up a diode circuit in multisim. So let's take a look at that. So multisim here. So this will be under instructor files and then ET302. And then this is the Diodes and Transformers lab. So we can look at the first one here. So this is the first circuit. So your lab book says you're supposed to set the battery voltage to 5 volts, resistor to 1 kilo ohm, and then measure the diode voltage, the resistor voltage, and the total current for the circuit. So you would set the voltage to 5 volts here. The resistor is already 1 kilo ohm. And then you can use the meters to measure the voltage across the diode, across the resistor, and then this meter will show you the total current for the circuit. So what voltage do we expect? First of all, is that diode forward biased or reverse biased?
Forward bias.
Forward biased, exactly. So what voltage do we expect to see across there? Yeah, about 0.6 volts, something like that. So we can run this and just check. Yeah, and sure enough, it's about 0.55 volts, something like that. And so then the rest of the voltage is across the resistor, and we can see the current there. So you're going to change the voltage around in the power supply. You're going to change the resistance around and see, hopefully that voltage across the diode is not going to change very much. It might change a little bit, but it's going to be approximately the same. Okay. Now, the next table it's going to be a very similar circuit, but this one is going to have 2 diodes in it. So you're going to look at that. And then this asks you to open a third circuit here. So let's take a look at this third circuit. Now this circuit is very similar to the first one, but there's one important difference. Anybody spot the difference here? That's right. The diode has been flipped around, so now it's reverse biased. So is there going to be any current flowing through there? No. Right. So the lab book says you enter the component values and make the measurements here. Now this part says, what is wrong with this circuit? So what they're asking is, they want you to notice that that diode is reverse biased. But I wouldn't necessarily say that that's something wrong with the circuit. Like I mentioned earlier, some circuits are specifically designed with the diode backwards or reverse biased on purpose. So I don't know if I would say that that's something wrong with the circuit, but that's what the question is asking about. Okay. Now, the next part of the circuit, or the lab, has parallel diodes. So let's take a look at that. well, it's got two circuits that are in parallel. Okay, so or two branches of a circuit that are in parallel. All right. So you're going to measure the voltage across the first resistor, across the second resistor, and then the diode, and make those measurements there. And then we're going to go on and look at some transformers. So we're going to open up another file that has a transformer in it. Okay, so this is a file, and it's got this transformer in the middle, and you've got the voltage coming in here from this voltage supply. When the voltage supply is a circle with a little sine wave in the middle, that means that it's an AC voltage supply. And this AC voltage supply is providing a voltage that's 141 volts peak. Okay, so if we look at that on a meter, do we expect it to say 141 volts on the meter? No, because the meter is not going to show us the peak voltage. So the meter is going to show us the RMS. So we can take a look at this. And so when we run this, yeah, we see about 100 volts RMS there. Okay? So we're going to look at that. We can look at this other meter that shows the voltage coming out. And now the voltage coming out is higher than the voltage going in. We had 100 volts going in. We had 400 volts going out. So is this a step up or a step down transformer? Step up, exactly. And we can change the turns ratio by double-clicking on the transformer here and changing that around. So this is a primary to secondary turns ratio. So this is the number of turns on the primary divided by the number of turns on the secondary. So this is backwards to the way that the ratio is normally described. So anyway, so this is 250 milli or 1/4. So it's really a 1:4 ratio of primary to secondary. So that means that the secondary is 4 times as many turns as the primary, and sure enough, you get 4 times the voltage out that you have coming in. Okay, so if you want to change the primary to secondary turns ratio, you can change it right here. So if we look at our lab book, it asks you to set the turns ratio to 1 and look at the AC voltage out, and then change the turns ratio and measure the AC voltage as it comes out. Okay, so you're going to fill in that table. And then you're going to do a very similar thing, but you're going to measure the current in and the current out and see how that changes. And then after that, you're going to actually deal with a real transformer. So we will have these real transformers to play with in the lab. The real transformers look like this. So the transformers have 2 wires coming in on the primary, and then they have 3 wires going out on the secondary. So what type of transformer is this?
It's a center tap.
A center tap, exactly. This middle wire on the secondary is the center tap wire. Okay, so what we want to do is we want to measure the resistance of the primary coil, and also we want to measure the resistance of the secondary coil. But there's a problem. The problem is that these coils are really just coils of wire, and they're not terribly long. So if we're measuring the resistance of those coils, and we're using this meter has these leads that are also wires. So we won't really know for sure whether we're measuring the resistance of the wire in the coil or whether we're measuring the resistance of the wire in the leads on the meter. So that's a problem. We want to know just the resistance of the wire in the coil, not the wire in the leads. So what we do to overcome that is that the first measurement we make is we just connect these two wires of the leads to each other. And then we measure how much resistance we have there. And it's going to be pretty small, so you're going to have to put the meter in the lowest setting. It's going to make that awful beep, but it's going to show you a number. So it's actually going to show you a resistance on that screen. And that resistance is the resistance of just these leads by themselves. So you're going to write down that resistance. That's called the tare, T-A-R-E. That's the tare resistance. That's the resistance of just the leads by themselves with nothing else. And then, once you know that, you can subtract that from the resistance that you get when you connect the coil, and then that way you'll know that whatever's left over is just the resistance of the coil itself. Okay? So that's what the book is going to ask you to do. So first of all, you connect the leads together, and you measure that, and that's the tare, and you write that down. And then you measure the resistance of the primary coil, and you subtract the resistance that you got for the tare up above, and then whatever's left over you write down here. That's the resistance of the leads. You do that for the secondary as well, and then you do that for the two parts of the secondary. In other words, the top wire to the middle, and then we'll call that winding A, and then the middle to the bottom, that would be winding B. Okay? And then down below, it says draw a transformer representation showing the resistance of the primary windings and secondary windings. So that's just a very simple diagram. It would just be a simple picture like this. You would show one coil for the primary and then a coil for the secondary, and you would put in the center tap as well. So say the primary had a resistance of 15 ohms, you would write 15 ohms there, and then from the top of the coil to the bottom, and then maybe the secondary had 3 ohms from the top to the middle. You could just draw something like that, and maybe 2.5 ohms from the middle to the bottom. You could draw something like that. So just a very simple picture that shows your resistances. Okay? And then could you measure the actual resistance to determine which wire is a primary and secondary? Answer that. And then what would the resistance be if there was an open winding? Remember, an open winding is a break in one of the wires, okay? So you would think about what the resistance would be if there was a break in one of the wires. And then we're going to actually hook up some voltages to this transformer and really see what the output looks like, okay? So you're going to hook the transformer to the function generator. You're going to hook up the black leads to the function generator and set it to 22 volts peak to peak and 60 hertz. And then hook up, you're going to hook up channel 1 of the oscilloscope to the black leads, in other words, to the input. So you're going to hook up the oscilloscope and measure that input that's going to your transformer. And then you're going to hook up a second lead from the oscilloscope to the output on the transformer. Okay? So you're going to actually have 2 channels on your oscilloscope displaying at the same time. You're going to have the input and the output both showing on the screen. And then you're going to measure those 2. So you're going to measure and record what the input voltage is and what the output voltage is. And then based on that, you're going to figure out whether this is a step up or step down transformer and what the approximate turns ratio would be. And then finally, you're going to connect the scope lead to the yellow and green wire. That would be the center tap, and measure that voltage there. Okay. Now this lab book is talking about green wires. When it talks about green wires, it's talking about the wires on the secondary. Some of these transformers have red wires on the secondary, but just know that when the book is talking about green wires, it's talking about the wires on the secondary. So just use the secondary wires, whatever color they are, okay? Yeah, and then there are a couple of questions related to the diodes and transformers that you can answer when you get to the end. So that's our lab for today. So any questions about that? All right, then I'm going to take attendance and let you go.